Okay, now let's come to the second part. So basically, for the second part, you can see that as far as for particle A, what is happening is that these three things together are applying forces like this. Okay. So to keep the particle A from moving like this, some external agent will have to apply a force which balances their vector sum. You're understanding the point? Because the net force on A should become 0. So if the net force on A is becoming 0, the only way that will happen is if something like this takes place now. Some external agent will have to apply a force in some general direction like this. Okay. So if the net force, that is the force due to the gravitational pull of B, C and D plus the external agent, okay, that has to be 0. By net force now we don't mean the net gravitational attraction, but we mean the external force plus the gravitational attraction. That has to be 0, okay, because A has to be held in place. Okay, so that means that the gravitational forces or the gravitational net force due to B, C and D has to be balanced, okay, by some external agent applying a force. Okay, so keeping that in mind, we can see that F external has to be minus of the vector sum of FB plus FC plus FB. Okay, so that means the magnitude of this external forces, external agents force, has to be the magnitude of the sum of these three. Okay. So this has to be that approximately like this. Okay. Now, so this is the answer for the external force on A. Okay, this is on A. Now, if you see B situation, it will be symmetrical, but C and D will be slightly different. Okay, so by symmetry, you will see that the external force on B will also have the same magnitude, but the external force on C and D will have a slightly different magnitude because their masses are 2m. Okay. So, hope you're understanding this point. So, by symmetry, you will see that for B, the magnitude of the external force to hold it in place is same as for E, that is this one. Okay. But for C and D, it's going to be different. So just now can see what is going to happen for C and D. So when you calculate this quantity here, it is very nearly equal to 3f in magnitude. It's very nearly equal to, if you calculate, it's 3.01 something. So from this you will see that for this also it will be the same. So hope all of you understood this point for the second part. So far for A and B, what we have discussed, hope you have understood it. Please let me know if there's any doubt. Now, similarly, by similar logic, try to calculate what's happening for the other two particles, C and D. Okay, so let's discuss the next part. So whatever, it doesn't matter if it's in some order, other order also. So for example, for D, now you can see that E will be applying a force like this, C will be applying a force like this, and B will be applying a force in this sort of direction. So the external agent will have to apply a force in some general direction like this, so that the net force becomes zero. Okay. So the similar analysis when we do on this, it's nothing very difficult actually. Okay. So you can see that on D, the forces by E will become 2 gm square by L square J cap. Because we'll take this as our y axis, obviously. Take this as our x axis. Okay. So that is 2f J cap, where f is equal to gm square by L square, or the quantity given to us 1.2 millinewton. Okay. The force applied by B that will be how much now? You can see the magnitude of the force applied by B will be again G into 2m into m into root 2L square. It's the same, gm square by L square, but this angle is 45. Okay. So again it is gm square by L square into cos 45 degrees I cap plus sine 45 degrees J cap. It's the same thing. So it is f by root 2 I cap plus f by root 2 J cap. Okay. So this is the force applied by B. This is the force applied by A. Now the force applied by C, this is the one which will become different. The force applied by C is a pair of 2m and 2m. You can see the magnitude of the force will become G into 2m divided by L square. So it's 4gm square by L square, or it's 4f. So this one will become 4f I cap. So now I have found the force applied by C, I found the force applied by B, and I found the force applied by A. Now the force applied by the external agent will be such that the sum of all these forces should be 0. Okay, because the net force is 0 because you're holding it in place. So that's it now. So you can see that FA plus FB plus FC this time will be how much? Just add these forces which I have tick marked over here. So they will be F into 4 plus 1 by root 2 I cap plus F into 2 plus 1 by root 2 J cap, or approximately 4.7 F I cap plus 2.7 F J cap. So that is this. That is equal to this. Okay. So therefore, the external force is negative of this. So it is negative of 4.7 F I cap. Okay. So the magnitude of the external force will just become F into square root of 4.7 square plus 2.7 square. Of course, this is an approximation where we have reduced to second place of decimal. So you will see that to do this calculation, it will come out to be okay. So that is million. So this is the situation of the body C, and again C and D will be symmetric. So whatever is the magnitude of the net external force on C, similar thing will be happening to D also. Oh, sorry, this is on D. So this is for the particle D. This is the analysis. Okay, so hope you've understood both the parts of this question, all of you. Now let's move on to the next few things to discuss. Okay, about gravitation. So next we will understand the concept of gravitational potential energy. So just like we have a formula for force, like that we have a formula for gravitational potential energy. So we have two particles of mass m1 and mass m2, which are at a distance of r. Okay, then the potential energy of the two particles system is given by the formula minus of g into m1 into m2 divided by r. We will learn this derivation of this formula in class 11th later, but this is the formula where of course g is the universal constant, so it is like that. If masses are in kg and r is in meters, then the potential energy is in joules. And the important thing is that potential energy is a negative quantity, and obviously energy is always a scalar quantity, remember, but it is negative because the force is attractive. So whenever a system has attraction force, it has stability. So it has high stability means it has attractive, it has negative potential energy or value of potential energy. Whereas we will see in electrostatics later that like charges repel each other, like protons and protons repel each other, or electrons and electrons repel each other. So whenever a system has repulsive forces, it has low stability and therefore it has a high value of potential energy. So potential energy in a system where there is repulsive force is positive. So that's not happening in gravitation, but for a system with repulsion, the potential energy Just a second, people. I'll reshare the board. Just give me a moment. Okay, so this is just a direct formula we have to understand. Just keep this in mind. Okay. So now let's see the typical application of this in a question. Now, for example, we have this situation that we have two particles, E and B, which are of mass 2m and m. And initially the distance between them is L, and their speed is 0. So A and B are released from rest at a position such that the distance between them is, let us say, L equal to something 120 meters, let's say. So given that the gravitational force between them at this point of time is 6.0 newtons in magnitude. Okay. Now, after being released, okay, at some point of time, the distance between them is now L by 2. Okay. The distance has halved. It's become half. So calculate delta U, the change in potential energy of the system A plus B, and the individual speeds of A and B at this instant. that is when R is become L by 2. Okay. So in both these parts, assume only mutual gravitational force acting. So just go through this question and try it out. So the formula that you'll have to use here, I'm just listing it for you on the side so that you can understand how to start approaching the question. So the formula that you'll require here is that gravitational force is given by Gm1 m2 by r square, and gravitational potential energy of a two particle system is given by minus Gm1 m2 by r. So use both these formulae. You'll require both of them here. So this is a slightly more advanced type of question. You can even say that this is a question which is in between your 10th level and 11th level. It's not exactly class 10th level question, but based on what we have learned so far, with a little bit of understanding and analysis, we should be able to work this out. It's not that difficult also. Okay, Adinath, let me check your answer. So here, see what is happening is initially you have 2m and m, which are at a distance of L. Okay. So the gravitational force that they apply on each other is G into 2m into m into L square. So that gravitational force of 2 times gm square by L square, that is given to us as 6 newtons. That's one thing. Okay. And L's value is also given to us as 120, was 120, right? 120 meters. Okay. So therefore you can see that the initial gravitational potential energy, which we can write as U, okay, the initial value of potential energy, okay, that is going to be minus G m1 m2 divided by R. So it's going to be minus 2 gm square by L. Okay. Now see, this is where this information will become very useful. So what we'll have to do is we'll have to compare. See, 2 gm square by L square is given to us as 6 Newton. Okay. And L is given to us as 120 meters. So therefore from here 2 gm square by L with a minus sign will simply become, we can write this as minus 2 gm square by L square into L. इसको हम ऐसे लिख सकते हैं potential energy के value को. So यहाँ से we'll substitute this as 6 newtons and this as 120. So the initial potential energy is becoming how much? It is becoming minus of 720 joules. So this is the value of the potential energy which the system, and this is the force. Okay. Now next thing we'll see is by the time the distance between them now changes. So because of that attractive force, A has suppose moved from here to somewhere here, and similarly B has moved from here to somewhere here. So at some instant later, okay, A is here and B is here, and the distance between them now has become L by 2. Okay, so by now A has gained some velocity v1, let's say, and B has gained some velocity v2. A's mass, remember, was 2m. B's mass. So at this instant, now the value of potential energy, which we can say is the final value, that is when the distance has become L by 2. So this is becoming minus G m1 m2 divided by R, where R is L by 2. So it's minus 4 gm square by L. So you can see that the potential energy has increased to double the value. There it was 2 gm square by L, यहाँ पे ऐसा हो गया. It has become minus 1440 joules. Okay, because remember, U initial, which was minus 2 gm square by L, we had calculated this was minus 720 joules. So that's why this is this. So the change in potential energy, which is the final minus the initial, will be itself minus 720 joules. So there is a loss of 720 joules of gravitational potential energy for the system, that is A plus B. So loss of this much means that there will be a gain of 720 joules of kinetic energy, again for the system A plus B. Okay. So now we can say that the change in kinetic energy plus the change in potential energy should be 0. By doing this, we are applying the concept of conservation of mechanical energy. And why we are able to conserve mechanical energy? Because on the system, that is A plus B, there is no external force to do work. Okay. Only the mutual gravitational force is acting. So that mutual gravitational force is an internal force. So not only can we say that the loss in potential energy is 720 joules, We can also say that with confidence that the system has gained exactly that much of kinetic energy as it has lost potential energy. Okay, so this is a very key concept here, and for example, this kind of thing will also become very important for us few chapters down the line when we are discussing work energy. So anyhow, so this is the initial state, okay, when r was equal to L, and from here it is going to this final state when r has become L by 2. So the potential energy has gone from this initial value here to this final value. Okay, so now how do we calculate the individual speeds? So from this we will see that the change in kinetic energy will be negative of delta U, so that will become plus 720 joules, because delta U was negative. Delta U was negative. There's a loss of 720 joules. So there must be a gain of this. Okay. So that gain in kinetic energy is how much? It is half of 2m into VA square plus half of m into VB square. So that is equal to 720 joules. Okay. Now the thing is we want to find VA and VB. So we have only one equation. We have to somehow generate another equation. Can anybody tell me where another equation will come from? So we need another equation involving VA and VB. So what is that? Where is that equation going to come from? One equation we are getting here. Getting this. This is the first equation. This is coming from conservation of energy. I'd like you to really think a little carefully about, you know, what what is happening in this system and what we have already discussed about the system in just the previous section. How we can make use of that discussion that we've had to generate one more equation. Yes, I'm checking the message. Just give me a second. हाँ मास तो ठीक है बेटा निकालना पड़ेगा, but the thing is that see we want to we want to this thing. What shall I say? We want another equation in VA and VB, ना? वो भी तो चाहिए. ठीक है, you can say mass is unknown, mass we can calculate because we know gm square by L square is so much. G is a universal constant, L was given to us, so we can always calculate M. So the problem is not with M really so much. Okay, the problem is that how we have two variables, na, VA and VB. M is like effectively a known quantity here. So any other concept, any other idea that we can apply about the system over here? So I'll give you a hint. We had just stated this fact about the system, that it is a system where there's no external force acting. We just written this down somewhere, that this system has no external force acting on it. That's why we wrote the conservation of energy. Na? Yeah, see, we had written this down over here. This thing, this fact that we've written here. So there's no external force acting. So mechanical energy is conserved. What else can be conserved? Very good. That's correct, Adina. So apart from mechanical energy, linear momentum will also be conserved. So that's why I said that this is a more advanced type of question, because you're mixing two concepts. You know the concepts. ऐसा नहीं है कि आपको पता नहीं है. But it's just that you're not used to mixing the two things together in the same question. So let's see how that works out now. So what's also happening here is that for the system, that is A plus B, the two particles, there is no external force. Okay. Therefore, linear momentum, that is linear momentum of the system, that is mass of A into velocity of A plus mass of B into velocity of B, should be conserved. Okay. Linear momentum is a conserved quantity. Now, initially, VA and VB were both zero. So the linear momentum of the system is how much? It's zero. So therefore, at the instant when R becomes L by 2, the momentum of the system should still be zero. Okay. So if this is moving at VA, so by conservation of linear momentum, we're getting the second equation. Okay. Now we can solve the two, and I'll show you how we can solve without even calculating the mass directly. Okay, so let's look at the two equations. So equation one was what, that half 2m into Va square plus half m into Vb square was, actually if you calculate the delta U, it was final minus initial. So it was minus G m into 2m divided by L by 2. This was the final minus the initial, which was minus G m into 2m divided by L. So this delta U in terms of these parameters is minus 4 plus 2. So delta U was minus 2 gm square by L. Okay. So this, remember, was change in kinetic energy was equal to negative of change in potential energy. So substitute this here now. So this is becoming plus of 2 gm square by L. So this is what our first equation is becoming parametrically. Okay. So we can also write this like this, that Va square plus Vb square by 2 is equal to 2 gm by L. Right, just cancel off the m over here. Okay. So this is what our first equation has become. Now, from equation 2, Vb is equal to 2 times Va. So therefore, Va square plus is this. Okay. So this is becoming how much? 3 times Va square is equal to 2 gm by L. So Va we can write as square root of 2 by 3 gm by L. Okay. Now we know that gm square by L square, 2 times of this was 6 newtons. We know this. Okay. So we know that gm square by L square is 3 newtons. Okay. So we can say that g square m square by L square is g into 3 newtons. Okay. So in other words, gm by L is square root of g into 3 newtons. So we can use that over here. Okay. So Va will become square root of 2 by 3 into g into 3 newtons. Okay. So that means we can say that Va in meters per second will become square root of 2 by 3 into 6.67 into 10 raised power minus 11 into 3. ये जो भी value आएगा, this will come in meters per second. Okay. And Vb is nothing but twice of V. So this is how we can do the calculation with minimum excess work. Okay, so I'll just minimize this a little. Okay, so people, we'll have to conclude here today. But hope you've understood this calculation fully. So unfortunately, because of the late start, I could not reach the portion of orbital motion yet. But see, the thing is, we need this concept of potential energy. Without that, we cannot fully understand orbital motion or even the concept of escape velocity. So don't worry, in the next lecture, we will pick up those two things. Okay? In the meantime, like a couple of you, I think had some doubts or things, you can send it to me on WhatsApp. I'll discuss. That's it for today's class, people. Next week, we'll pick up from this point and we'll discuss about orbital motion, Kepler's laws, as well as the concept of escape velocity. So if you like, you can read ahead about those from your textbooks, but we'll discuss about that.